So, as before, I really want to thank the organizers for this wonderful opportunity to speak about my research and also for the wonderful conference that we're finding ourselves in here. Today, I'm talking to you about gap solitons in these topological models. So before anything, I should start talking about collaborators and the group back in Birmingham. So my supervisor, Hannah Price, and the rest of the group here, working back in Birmingham, but also with very heavy correlations with Jacopo, of course, in the University of Trento. And the two people contributing the most to this work is Holly from our group, helping a lot out with the numerics, and also then Jacopo for most of the theoretical contributions. So I wanted to give a brief content for the talk. So we're going to go through the main goal, the background of this work, before looking back at exactly what we're talking about, some previous work, and then some results that we have found ourselves on this topic. So to begin, we want to start talking about the main point of this talk, which is the linking of these two topics. So the main interest is going to be these things, these topological band structures. So these are structures that I will explain a little bit later, but many people have, there's been a bit of an introduction here in the conference already. And of course, these have been studied very well in the sort of single particle case. And there's very rich physics there. But then we also have nonlinear physics, which has been much more talked about in this conference, specifically terms that you add into your Hamiltonian that have some sort of density dependence in some sort of mean field interaction terms. And these have been very well studied, as I'll talk about a little bit later as well, in trivial band structures, topologically trivial. And the idea then is, if we can combine these two things, of course, that's going to lead to some potentially new physics, which is always very exciting. But first, we should probably go into a little bit of the context behind these two topics. So the first one I want to talk a bit more about is topology and topological band structures. So the idea behind these is that topological band structures are ones that have global invariants associated with each one of the bands. And those global invariants are linked to the local properties that the bands can have. So a big local property that we're concerned with, and that has been talked about a bit in this conference before, is the Berry curvature, which, to put very simply, is a relationship, is a function that can tell you about how eigenstates in the band change phase depending on parameters that sort of define those eigenstates. Particularly here, we're mostly concerned about this block momentum. And what has been sort of talked about a lot as well is that this property can manifest in experiments when you look at it as a source of an anomalous velocity term, when you look at wave packet dynamics, so ones that are formed from these sort of topological band structures. Jacopo talked about this earlier. But of course, then you have the other side, the global invariance of the band, and specific models that again have been talked about are these models that have non-zero Chern number. And we can say that these sort of bands which have non-zero Chern number are topologically non-trivial. And in particular, you can extract the Chern number out as a global property because you have to integrate this Berry curvature over the entirety of the Bullerbin zone. So you need to know about the entirety of your band in order to get some Chern numbers out. And of course, that provides us a nice link between the local and the global properties. But most importantly, and has been sort of highlighted, is that these Chern numbers can't be changed unless you close the band gap in your band structures. And then this leads to the very well-known situation where if you have some boundary of a non-trivial topological phase and then a trivial topological phase, then you're going to get the measurements of edge states. Was that a question? This definition, so there's a lot of maths behind this. So this can be extended to higher even dimensions. So you can go, something that my supervisor Hannah really loves is synthetic dimensions. We talked about it in 4D. So this definition, whilst it looks slightly different in 4 dimensions, can be extended. In odd dimensions, not so easily, but you can still get topological features in odd dimensions, an SSH model, for example. So, okay, awesome. So now that we've sort of spoken about this, another big thing that we're very fortunate about is that topology has been studied in a lot of different photonics contents, obviously seen a lot in this conference. The ones that I've got on here, though, are mainly sort of these measurements of edge states. So we've seen edge states being measured in photonic crystals. We've also seen them being measured in these chiral waveguides. These are essentially waveguides that you turn and they generate artificial magnetic fields. Obviously, your photons don't really respond to real magnetic fields, so you have to be a bit more creative. But again, these measurements of edge states have been very clearly shown. But one thing that I'm going to highlight the most in this talk is this measurement of the Berry curvature, again, due to this wave packet drift, this anomalous velocity. And so to go into a little bit more detail with this, we want to start talking about what the Berry curvature is in the context of these wave packet dynamics. And one very good way of thinking about this is that the Berry curvature can be seen as a momentum space magnetic field. So if you look at the semi-classical motion of a wave packet, so the center of mass of that wave packet, you see that you get this group velocity term, but then you get this anomalous drift term that, in my opinion, initially seems like it comes out of nowhere. But if you take on this approach, that this Berry curvature can be interpreted as this momentum magnetic field, again, the previous picture, where you apply some force in a particular direction, but then the force that is exactly perpendicular gets applied, this velocity, what you can do is you can actually see that this Berry curvature generates a sort of momentum space equivalent of a Lorentz force. So we have the sort of famous one where if you have some electron moving in a magnetic field, which is some initial velocity, it's going to feel this anomalous force. And in an equal exchange, if you have some initial force, some constant force being applied, your Berry curvature is going to cause some anomalous drift. So if you switch the two, you switch some sort of rate of change in momentum to rate of change in position, these two have a nice symmetry involved with them. And of course, we should be talking about Chern numbers here, and how does this link to Chern numbers? Berry curvatures link to Chern numbers in some way. And so what you can do is you can form your wave packets not with very sharp peaks in momentum, but actually very uniform distributions in momentum, where you're taking a wave packet formed from many different states in the momentum space. This is what's shown here, so some sort of constant distribution for your bosons or your light, and you can look at the average velocity terms that you get. And what's going to happen is that this group velocity contribution on average is going to completely cancel out. And the way to think about this is that for the contribution that a single K state, a single K sort of momentum state has in one direction, you're going to have an equal filling that's going to have an exact opposite velocity component that will always cancel out. So the wave packet will spread, but it won't move in the center of mass way. But the interesting part, again, if you apply this force in a given direction, there's going to be this anomalous velocity term which is not going to go away on average. And in fact, because you've got a uniform filling, again, you know about the entirety of the band, you're going to get the Chern number back out. And in fact, this is very useful because you can use it due to this vanishing in one direction but sort of constant quantized motion in the other to measure the Chern number. And this has been done in cold atoms experiments, and it's a very interesting insight. But this is all topology. There was another side of the slide which is talking about these gap solitons that have been mentioned a few times before, but we need to talk about these as well to see if we can link them. And of course, the highlight is that this is in trivial band structures. There's no topology here. But the idea is quite simple. As we've talked about a lot, and everyone's seen this, this describes the motion of light, Bose-Einstein condensates, mean field, traveling through nonlinear medium, etc., etc. But as we might also know, you can get a balance between these two terms, the diffusion, the sort of dispersion of your wave packet and the attraction that you can get in an interaction, and that can form solitons, localized, self-supporting wave packets. And this is very easy, in a sense, if you have attractive interactions that can balance your wave packets spreading out. But it's not so easy, although it can still be done, in repulsive interactions. But if you're smart, you can use this potential to your advantage in the way that if you have some periodic potential, arbitrarily periodic, think about it in a sort of nearly free electron model, you go from having some sort of free band structure that has a constant, positive effective mass, to then getting regions near the band edge where your effective mass will become negative. And the idea then becomes, if you have a negative effective mass, but repulsive interactions, the actual effective interaction is going to be attractive. And so that means that you can still get solitons out, and these gap solitons mediated through the lattice potential are called gap solitons. And these have a lot of interesting features, the first of which being that they lie with energies completely in the band gaps. Yes?
What is this energy landscape?
The what, sorry, the energy?
This energy as a function of K?
This one?
No, your curves.
The dispersion relation.
For what?
So this one is a free electron, so just a free one, and then you apply some arbitrarily small periodic potential, and then you get the opening of band gaps. And so you just, it's an arbitrarily just nearly free electron, just put in the small thing, so yeah. No. This is just, if you have some lattice and some linear case, then your periodic potential will open up band gaps, so yeah. Okay, no problem. So yeah, these gap solitons have a lot of interesting features, but the main ones is that they live in the band gaps of the underlying linear structure. So this here is a power energy curve, so now your soliton can have sort of arbitrary normalization in the power, and you can see these curves are the existence curves, and this nice block in the middle is where the linear energy values would be. And you can see, depending on the sign of your nonlinearity, you get solitons bifurcating up or down from these things because they're mediated by the lattice. And another important thing is that because I can sort of get arbitrarily close to turning this parameter off, my solitons at very low powers or very low interactions actually are envelopes of the underlying block states at these band edges, because that's where your effective mass is negative. But with these gap solitons, we can look at them in photonics experiments, and thankfully, again, they've been studied very well. This is an experimental realization in a photonic crystal, where they start by putting in some initial excitation and letting it disperse without turning on the lattice. But then as soon as they turn on this lattice, you see that at low powers, you get this sort of localized gap soliton that sort of respects the structure of the underlying lattice. And then as you get to higher powers, higher power soliton, you get to more localization, as is sort of the standard thing with solitons in general. And so with that, after explaining the context, we can probably go back to our main goal and say, well, one avenue we can do to kind of link these two things together is say, this is a band structure with some negative effective mass regions, but it has this extra topology added onto it. Can we get gap solitons, and are they sensitive to the Chern numbers at all? And people have done a little bit of previous work on this. One thing I should mention very briefly, but I will not go into detail on, is some work by Reshman and his group, where they looked at this idea of nonlinear thallus pumping. I don't want to go into the gross details of all of this because it's rather complicated, but it is related to our work, and they indeed find similar solitons with these sort of power energy curves as described, and they find this sort of quantized motion, but there's sort of another piece of work that is a little bit more aligned with the research I'm presenting today here. And this is gap solitons that were found theoretically by Marzullo, where they looked at this topological model that's defined on a Lieb lattice. And for the most important things, you can see this band structure is here, the Chern numbers are labeled, and you have these nice negative effective mass regions. And they did indeed find these solitons. They found them respecting all the normal properties of gap solitons we know, with momentum distributions at low powers that are localized at those negative effective mass regions. And then they didn't stop there, but they actually said, well, what happens if we look at the dynamics of these solitons? And it turns out that they actually follow this Berry drift, this anomalous velocity drift that we talked about in the linear case. But the weird thing is that these solitons exist in the gap. They don't belong to a band, so why are they following a linear drift that's associated with a given band? And so this was presented, these motions were sort of mapped very well, and then the idea was that, maybe we can take it from here and see if we can investigate this further. And so we get on to some of the current work and results that we've got. And before we sort of talk about what happens when we find our solitons, we should probably choose a topological model that's rather useful. And so our underlying model is the Harper-Hofstadter model. So to give a very brief overview of the wonders of this model, the Hamiltonian is given here. And this describes a particle that is bound to a square lattice, but is under the effect of some sort of magnetic flux. And this magnetic flux alpha gives rise to these complex hoppings, and the parameter alpha is incredibly important in this model. Due to the sort of discrete nature, if alpha takes on these rational values, alpha actually sets the size of the magnetic unit cell, we call it. And the way to think about it is like this, where this phase hopping now, instead of just hopping and then it being periodic whenever you choose to hop, instead you have to hop q many times before your phase returns back to what the wave function looked like however many hops ago. So your unit cell elongates. Obviously, things get smaller. So when it elongates, it depends on this value of alpha q, and this sets sort of what the band structures look like and what I've been showing previously. This is a topological model, but most importantly, it's actually a very rich model. The model that was shown with previous work actually only has Chern numbers plus minus 1, but here, this very famous Hofstadter butterfly tells you the sort of many different band structures you can get by changing your alpha to many different rational values. This beautiful structure here tells you how these band structures change, and as you can see by this labeling, this is the Chern numbers. You can get many bands with many different Chern numbers. So we wanted to use this, and then we can start looking at what we found with our solitons. Of course, we started by taking this Harper-Hofstadter and adding in this nonlinearity, particularly a saturable, because we eventually want to go to quite high powers. And as a result, we found our nice solitons, and we decided that a good check would to be checking it against the results of Marzullo, specifically seeing if these drift in the same way that we would expect for low powers. And thankfully, we do find these gap solitons, and they do seem to have this drifting parameter. So, of course, there is a slight deviation. This green line here is the predictions that you would get from the drift. These are the block oscillations. We're applying a force purely in the x direction, so we're expecting these block oscillations in the x. But then we get this drift in the y with some deviations, and this is essentially due, you can ask me, but the basics of this is that it's due to some nonlinear damping that you get quite naturally out of this. But this is previous work. We want to try and do something slightly better, and it goes back to the band filling that we had talked about a while ago that people used to measure Chern numbers. And so the idea we had is rather simple. If we take a higher power gap soliton, it's going to become more localized, and if it's going to be more localized, it's going to have a more uniform spreading K-space. Just Heisenberg uncertainty principle. And in a way, you can think about this as an energy sense. You sort of make your power higher, higher interaction energy, higher energy soliton, and then you have an energy that is much larger than the bandwidth that you're actually bifurcating from. And so the soliton can't resolve itself. And so with that, you can start using this Harper-Hofstadter with many different alphas. Here we've chose this 1 over alpha. And from this energy argument, if you have a very flat band, and a very high energy soliton, you would expect a very nice filling of the momentum space. And so you can use these very flat bands at very high powers, and we should be able to get some uniform filling. And do we get quantized velocity? Now, I wouldn't be presenting this if we didn't, because indeed, if you get these really high power solitons that are really localized, then you can start to see that this filled band prediction given by this black line here has incredibly good agreement with the soliton evolution itself. The filling here is practically uniform. And then this drifting here, you can ask me a bit more details about it later, but essentially we're not having a full filling of the band, so we get a little bit of drift in our X, even though it should be poorly in this direction. And these oscillations are actually due to ZB oscillations. So these higher power solitons get this quantized drift, and we can match these predictions for sort of linear theory, and the numbers match up very well. But of course, this is just a Chern number of -1, as sort of shown here from the first band. We should really be able to have some more candidates. So again, we turn to Harper-Hofstadter. We get a very nice band structure with a very flat band in the middle, but with Chern number -2 now, we can change it around and see if we still get quantization. And of course, we get these still very heavily localized solitons now. But here we've bifurcated it from a much higher band. In fact, the 6th band gap is where we're at now. And we still get incredibly good agreement with this filling, but with some oscillations on a slightly larger time scale. And so the most important thing here is that we found these solitons at very high interactions, very far away from the linear case, that are very stable and drift in a very controllable manner only due to the topology of the bands. You turn this topology off, you don't have it, you don't get this movement. And so with that, I'd like to make some conclusions and sort of talk about what we've really seen here, which is that we've already seen very good evidence that low power gap solitons respect some local properties of the band, even though they exist outside of the band and are nonlinear objects themselves. And our work said, well, if we take these higher power solitons, we actually get uniform occupation. Interactions are all the way up, but we still see uniform occupation, and we still get velocities that are quantized by the Chern number, even though we've completely departed from a single particle linear predictions. But there's still a lot of open questions about this. Why do they do this? We don't fully know at the moment. That's what we're currently investigating. But also, does the soliton structure link at all to the topological properties that are very robust from this initial structure? More than anything, though, we're very excited that these solitons are as controllable as they are due to the topology. And in fact, this motion can persist for incredibly long time scales and is very highly controllable, which is very experimentally viable, and could potentially be used to actually measure Chern numbers in a drift measurement sense like we've done in cold atoms. But I think saying it is one thing. I would rather show you what this motion, how sort of controllable this motion is, and maybe as a nice end to the conference itself, I decided to make a small little animation using our solitons numerically. So with that, I'd like to finish, but I would also like to say, as being the privilege of the last speaker, that I think I speak for everybody here, where I would really like to thank the organizers for this amazing conference, and I'm sure I'm speaking for everybody where I say that I've had an amazing time, and that it's been brilliant seeing so many wonderful pieces of work. So thank you very much.